all of the same rules that we've just been looking at for quadratics apply for cubics as well, and quartics and quintics and so on. I'm not going to prove this because it's longer, but in exactly the same ways we did for quadratics, you can expand out brackets with the roots in and prove some results for the relationships between roots and coefficients. What we find is that for a cubic equation, the sum of the roots, again, is equal to minus b over a. Same as for a quadratic, and this is the same for all polynomials. So the sum of roots is always equal to minus b over a. You then follow a pattern from here, so you get minus b over a, positive c over a for the next one, negative d over a for the next one, and so on. The next one down is the product triples, which for a quadratic is just, so product pairs. For a quadratic, this is just the product of the roots. But this one is the product pairs. There are three combinations of these, so you can have alpha times beta, alpha times gamma, and beta times gamma. Sometimes we'll write this as sum of alpha beta. Finally, there's the product of the roots of a cubic, which is equal to minus d over a, and this is just alpha beta gamma. But given this cubic, we're being asked to write down these results. So the sum of the roots is always equal to minus b over a. B is minus 7, a is 3. This will give you 7 over 3. Sum of the product pairs is equal to c over a. C in this case is 4, a is 3. And finally, the product of the roots for a cubic is minus d over a. D is 10. This is minus 10 over 3. I've got the U try and I'll put that up in a few seconds. Just like we did before, if we're given the roots, we can work out the coefficients of our equation. Again, you can put them in brackets if you really want to, but I'm going to use the sum and product of roots. Start with the sum of the roots. Adding these together, surds cancel out, and you should get minus 1. And this is always equal to b minus b over a. Looking at the product triples now, so there's three combinations of these I can have. I have 3 times minus 2 plus root 6. I can have minus 2 plus root 6. That's minus 2 minus root 6. Or I can have 3 times minus 2 minus root 6. Three combinations now. So expand these and work them out, although you could type it into your calculator. Minus 6 plus 3 root 6 plus 4 plus 2 root 6 minus 2 root 6 minus 6. Let's cancel. And from the last one, we get minus 6 minus 3 root 6. Again, those surds will cancel out. Here I've got minus 6 3 times and then plus 4, which will give me minus 14. And this one is equal to c over a. Finally, I've got the product triples, or the product of the roots at alpha, beta, gamma. This is 3 rationals. Now we've actually done most of this multiplication already. We've expanded those brackets out here, and so we got this result here. That gives us minus 2 for this. This is 3 times minus 2, which gives me minus 6 or minus d over a. No fractions involved, so we're going to choose a equals 1. It's straightforward. So that means b equals 1. It means c is minus 14. And d is 6. Again, pause the video, have a go at the U try, and I'll reveal the answer in a few seconds. Now, similar to quadratics, for a cubic, if you find that one of the roots is complex, one of the other roots will be the complex conjugate of that. But for cubic equations, they should have 3 roots. If you were to solve this equation in your calculator, put in 1z cubed minus 3z plus 4z is 2. We'll get 3 solutions. We get 1 plus I, and 1 minus I. Notice here, obviously, we've got a complex conjugate pair of 2 of the solutions, but the third solution must always be real. If you think about cubic graphs, we ignore repeated roots. The options you can have 3 roots on the left, 3 real roots on the left-hand side. And on the right-hand side, we've got 1 real root, which corresponds to 2 complex roots. First off, example 2 here asks us to show that this is a root of this equation. I'm going to call this f of z. We're going to use the factor theorem from single maths to show this. So all we need to show is that if I substitute in 2 minus I get 0. Here I'm not going to show the expanded out, although because it's a show that you might want to. But if we do expand this out and collect it all up, you do get 0. Do a little conclusion to tie us up at the end. I'm going to say therefore, as f of 2 minus 1 of 0, 2 minus 1 is a root of f of z. It then asks me to find the other roots of the equation. If I know that 2 minus I is a root, I can immediately write down another root as 2 plus I. I can then use any of my sum and product formulae to work out the value of the third root gamma. I'm going to use the sum, which I know is equal to minus b over a. Alpha is 2 minus I, beta is 2 plus I, gamma I don't know. B in this case is minus 10. And A is 3. Yeah, I should cancel out, but this gives me 4 plus gamma equals to 3. And if I minus the 4 across, I get gamma is minus 2. Pause the video, have a go at the U try. Final example is this here. So it tells us one root to the equation, tells us some information about the equation, but not all of it. And it wants us to find the values of A and B, confusingly in different places to the original A and B, and the other roots of the equation. I'm going to start off with the fact that I know that if 2 minus 5i is a root, I can immediately write down 2 plus root 5 is a root. 5i, sorry. Even though it says find the values of A and B and the other roots of the equation, I'm not going to do it in that order. I'm going to find the roots first and then the values of A and B. Now, looking at the equation, we've got minus 7 in the C position. So C is the sum of the product pairs of your equation. That's equal to, so the sum of the product pairs is equal to C over A. Let's substitute in what we've got. So alpha we've got is 2 minus root 5i. Beta is 2 plus root 5i. Plus beta times gamma. Gamma is what we're trying to find. 2 minus root 5i gamma again. And that's equal to C over A. Well, C is minus 7. And A is 1. Let's expand this out and tidy it up a bit. So expanding this out gives me 4 plus 2 root 5 I minus 2 root 5 I and then minus 5I squared. Plus we've got 2 gamma plus 5I root 5I gamma plus 2 gamma minus root 5I gamma. So the roots cancel out. And finally, we've got same thing again. Minus this line, so 2 gamma. Already done that one, sorry. And that's equal to minus 7. Tightening this up a bit, so my surds cancel out here as well. So I've got 4 minus 5I squared is minus 1, so that's 9 plus 4 gamma equals minus 7. Set is equal to minus 7, and minus the 9 divided by 4 gives me gamma is minus 4. Once I've got that, it's not too bad to work out the coefficients of A and B. So for A, that's the coefficient of Z squared. That's where B normally is. So I'm going to use the sum of roots equal to minus B over A to find that. We had 2 plus root 5I minus root 5I minus 4 for gamma equals to minus B over A. A is 1. Minus B. Thirds cancel, but 2 plus 2 minus 4 is 0. And in our case, actually, instead of B, it's A. This tells me the value of A is 0. Finally, for their value of B, I'm going to use the product of the roots. Alpha beta gamma. So that's 2 plus root 5 I 2 minus root 5 minus 4. Now, instead of writing this all again, I have already done this calculation earlier on here. So I know that this is equal to 9. I've actually got 9 times minus 4, which is minus 36. This is equal to minus D over A. In our case, A is 1 and D is B. So we can work out a value for B is 36. Pause the video, how I got the U, try it, and I'll show the answer.